I think we just cracked that walnut. That's good. Speaking of cracking walnuts, I watched this YouTube video recently where this woman she's like a forager and she collected all these walnuts and she explained to me, like in a very excited tone, why it's good to let the maggots get to the walnuts first because they loosen up the husk and then you can roll the walnut around under your boot and the husk just falls off and the maggots never get into the inside of the walnut. So then you take your walnuts and you boil them in a pot and the remaining walnut flesh comes off in the pot and then you can take your walnut and put it into a dehydrator. And if you put it into a dehydrator for 24 to 48 hours, it'll keep forever. And then you can have walnuts whenever you want walnuts. But what's more is the stuff from the pot when you boiled off the husk is totally toxic. It's amazing. So as we crack this next nut, I want you to think, if you do prepare walnuts, you can take the boiled off extract from walnut husks, and as a toxic stew, it's a natural herbicide. And if you ever notice that nothing ever grows underneath walnut trees, that's the reason. Anyway, let's move on. The more you know, knowledge is power. So inverse square law. You should watch that woman. I don't really know what her channel is or anything. It's just in my newsfeed. So she keeps on coming back to me and telling more things about mushrooms and things that I probably shouldn't try to eat, but I still think it's fascinating. All right. If I talk about the force due to gravity as a function of how far we are away from, I'll just say distance, away from a massive body like the Earth in meters, we've said in the past that F big G drops off, and this is what we were looking at before with proportionalities, as a function of 1 over r squared. And so that means that as you get farther and farther and farther and farther and farther and farther away, we've got a 1 over r squared proportionality that happens, not a direct proportionality. 1 over r squared is an inverse square law. But the thing that we would say in math class is that there's an asymptote here, which means in the limit where r approaches infinity, notice in the limit where r approaches infinity, that fraction never really becomes 0. So no matter where you are in the universe, according to this proportionality, the gravity of every other thing technically affects you. A lot or a little though, right? Like basically, since it drops off as an inverse square law, any distance away from a mass, it doesn't really affect you that much, which is why we don't really feel the pull of Pluto here on Earth. We don't get like Pluto tides in our oceans or anything like that because it's minuscule. It drops off as an inverse square law. And then we talked a little bit about Cavendish once before, but if you are a distance r away from the Earth, or if you're a distance 2r away from the Earth, this time I drew the diagram for you, or you're a distance 3r away from the Earth, this idea of the inverse square law comes about for geometric reasons. And we can make the diagram more complicated than this, but this is a good enough for now kind of diagram to say that if I were to make squares at those different distances away from the gravitational source, as gravity gets projected out into the universe, what we would find is that at 1r, 2r, and 3r, the relative areas of those projected surfaces end up having a relationship so that if the first square has an area of 1a, the second square would have an area of 4a, and the third square would have an area of 9a, which again means that the gravity is being spread out over a proportionality of 1 over r squared, this inverse square law proportionality. Now, when we talk about two masses, force of universal gravitation, getting me down. Force of universal gravitation is a mutually attractive force. So this F big G, Gm1 m2 over r squared, is actually an example of a Newton's third law kind of force, where we would have, say, a planet. Here, I got my planet here. I don't know how oblate spheroid it is, but let's just say I have an object sitting on the surface here. You know that the object sitting on the surface is attracted to the center of the Earth, but the center of the Earth is also attracted to that object. The fact that there's a mass imbalance means that even though they might be attracted by a mutually same magnitude force, the mass imbalance is going to mean that we experience a lot of acceleration around the Earth, and the Earth doesn't experience a lot of acceleration towards us. That's it. Okay. So we've kind of been there and talked about that before. I want to talk about this other thing though, because honestly, it makes me think a little bit of decibels. Because when I think about the Earth and the way that the Earth projects gravity out in all directions, and I think about sound, and I think about the way that sound waves get projected out in all directions from a speaker, it is sort of like the same like isotropic radiation going out in all directions. So when I think about a gravity source, let's just make this little nugget be a gravity source. And then I think about a sphere of space, not a pyramid like the one that I just drew here, an actual sphere. So these circles here aren't circles; they're three-dimensional spheres. Okay, like if you want to make them a little 3D-ish just to convince yourself, that's fine. But they're spheres, not circles. Okay, so when I think about these spheres, I would have an R1 and I would have an R2, not D2, R2. And that means that the surface area of these spheres would have the form A1. The area of the smaller sphere is 4 pi R1 squared. And the surface area, let me zoom in on that because like I don't want anybody to miss this. The surface area of the larger sphere would be A2 equals 4 pi R2 squared. Now, what we often want to do when we talk about sound intensities is to compare the intensities to one another at different distances. And we talk about sound wave energy radiating out like a sphere from a sound source. In this case, we're not talking about it's not the same thing at all. This isn't sound wave energy. This is gravitational field intensity. But just like sound can have an intensity, gravity can have an intensity. So what we can do is we can sort of make an analogy in that way with our math. And what we could say is that the area of 1 over 2 is equal to 4 pi r1 squared over 4 pi r2 squared. And we could say that the areas over which the gravity is being spread, area 1 divided by area 2, is going to look at all the canceling that happens here. Isn't this gorgeous? Oh my gosh. This ends up being like the 4 pi is gone. R1 squared over R2 squared. If R2, I forgot to square the R2. If R2 equals 2 times R1, in other words, if the radius of the outer sphere has twice the radius of the inner sphere, what we're saying is, let's plug that in. A sphere with twice the radius would end up having R1 squared over 2 times R1 squared. Remember those proportionalities we were looking at earlier? You end up getting A1 over A2 equals R1 squared over 4 R1 squared. In other words, A1 has 1/4, the area of A2. But what we could also say is that the gravity spreads out over 4 times the area. And so the reason that I would want to bring this up with spheres is because honestly, this proportionality of the gravitational field spread over the surface of a sphere is actually a stronger argument for the inverse square law than the pyramid argument. Because we don't really think about gravity being projected out as like a flashlight into the universe from a planet, like a focused beam. We think of it as more like a spherical projection that comes out from the planet, almost like light from a light bulb going in all directions, or sound from a speaker going out in all directions. This idea of the inverse square law is better explained as a proportionality of spherical surface areas. That's all I want to say about that one. Yeah. Oh, yeah. So this 4 here, remember we were talking before about how, I'll do it in red so that it doesn't interfere, how 1 over 2r squared is equal to 1 over, you got to square the 2, and then you also have to square the r. Yeah. Okay. Anyway, the idea of spherical radiation is something that comes up. I've already mentioned in this conversation gravity, sound intensity, light intensity, and honestly, I'm not going down this rabbit hole right now, but if this is also something that could describe light intensity proportionalities, can you believe that if we could look at a star and make a educated um, inference about how big that star is, how much light is coming off of that star, we could tell something about how far it is away from us by looking at its intensity relative to what it might be at if it was closer to us, based on its composition and size and its gravity. Like, this is kind of a big thing in terms of cosmogony too. Not the direction we're going in right now, but like, this math model is a good math model.